Good morning, dear students. So today we shall understand what is Ampere's circuital law and also its applications. Ampere's circuital law and its applications. Ampere, he was a French physicist, chemist and great mathematician. At the age of 12 years itself, he could master advanced mathematics. He was so genius and he contributed a lot for the development of magnetic effect of electric current. He got attracted towards the discovery made by Hans Christian Ørsted, magnetic effect of electric current. So later on he started working on it and he proposed a law which is considered to be very significant. In finding out magnetic field around a current carrying conductor. Compared to Biot-Savart's law, Ampere's circuital law has a lot of advantages that you will understand what are the advantages of Ampere's circuital law over Biot-Savart's law. And it is just like Gauss law in electrostatics. Let us understand what Ampere's circuital law explains. If you consider a current carrying conductor, it may be of any shape. It may be in the form of a cylinder, it may be in the form of a rod, it may be a wire, okay? It is carrying a current. Let I be the current flowing through the conductor. Ampere's circuital says that the line integral of magnetic field around a closed path in free space is equal to mu naught times the total current passing through any surface enclosed by the closed loop. The line integral of magnetic field around any closed path in free space is equal to mu naught times the total current passing through any surface enclosed by the closed path. Let us understand that through an example. Let me consider currents. This is the surface. This is the current. I1, this is I2. This is I3. This is I4. And let this be a boundary which is enclosing all these currents. I just take an element here, dl, an element dl, and the magnetic field is acting in this direction. Let the angle between them is theta. Then, according to Ampere's circuital law, the line integral of magnetic field around this closed path is equal to mu naught times the total current passing through any surface enclosed by the path. See here we make one convention. See when you take your right hand with the thumb pointing the direction of current, see if the current direction is along the thumb, then current is taken to be positive. If it is opposite, it is taken to be negative. Therefore, I1 and I4 are taken to be positive, whereas I2 and I3 are taken to be negative. See, therefore, I1 minus I2 minus I3 plus I4. See, this is the net current enclosed by this loop. Net current enclosed by this loop. This loop, yes. What actually B dot dl? B dl cos theta. See, this is B dot dl is equal to B dl cos theta, where theta is the angle between length element and the magnetic field. Suppose if the conductor is a straight conductor, then you just imagine a loop, around this straight conductor. See, we call this loop as Amperian loop. See, therefore there may be a boundary, real boundary or imaginary boundary. So using that boundary, see, we can determine what is the magnetic field, but that boundary should enclose the current or current carrying conductor. So we call this loop as Amperian loop. So Ampere's circuital law says that, it states that the line integral of magnetic field around any closed path in free space is equal to mu naught times the total current passing through any surface enclosed by the closed path or enclosed by the path. Okay, here I1, I2, I3, I4 are the current which is enclosed by the path. Yes. See, here we have made one convention. See, you take your right hand, please take your right hand, thumb pointing the direction. See, if current is along the direction of current, if the thumb direction and current direction are same, then the current is taken to be positive. If the current direction is opposite to the thumb, it should be taken as negative. So you must take this surface, close the surface as the reference to find out what is the direction of current. Okay, to take whether positive sign or negative sign to the current associated with the conductor, right? See, therefore in this case I1 is positive, here I2 is negative, I3 is negative, this is going outwards, therefore this is also taken to be positive. So now let us take specific examples for understanding Ampere's circuital law. So therefore the line integral of magnetic field around any closed path in free space, around any closed path in free space is equal to mu naught times the total current passing through any surface enclosed by the path, enclosed by the path, enclosed by the path. The path you have taken, you know, see this is the path you have taken. See here, this is a imaginary closed path. Okay, now let us take up the applications of this. Magnetic field at a point, magnetic field at a point due to a long straight conductor, a long straight conductor carrying current, Now I just consider a long straight conductor carrying current I. Select some point P is at a distance r from this current carrying conductor. See, to determine what is the magnetic field at this point, I just imagine Amperian loop of radius r, and the magnetic field here, see this is the line element, and the magnetic field here is tangential to the line element. Magnetic field is tangential to the line element or length element. So then let us make use of Ampere's circuital law. B dot dl is equal to mu naught into I. See, this is here B and dl are along the same direction, that is theta is equal to 0 degree, which implies cos theta is equal to 1. See, therefore B dot dl is equal to B dl cos theta, which is equal to B into dl. B is magnetic field, it is constant and it is tangential to the Amperian loop. See, therefore I just take line integral to dl. When you add the line elements, you will be getting circumference of the circle. Okay, see, this is equal to mu naught into I. See here when you integrate, when you add all the line elements or length elements, you will be getting circumference of the circle 2 pi r. See, therefore you will get B into 2 pi r is equal to mu naught into I, or B is equal to mu naught by 2 pi I by r, or even you can write like this: B is equal to mu naught by 4 pi 2I by r. See, this is the magnetic field near a long straight wire carrying a steady current I. Here the current is steady, remember. See, therefore let P be a point which is at a distance r from the straight wire carrying current. To determine magnetic field at B, I just imagine Amperian loop of radius r with conductor or with the wire passing through the center of the loop. The magnetic field is always tangential at all points on the Amperian loop, and the dl, the length element, and B are parallel to each other. See, therefore the angle between them is 0. Since B is constant, we have to take summation over the length element. The summation of length element or line integral of length element gives you 2 pi r circumference. So therefore you will be getting b into 2 pi r is equal to mu naught into I, or b is equal to mu naught by 2 pi I by r, or b is equal to mu naught by 4 pi 2 I by r. So let me consider a solid wire. So I just enter inside this wire. I just imagine I am entering in this inside the wire. I just take the cross section of the wire. See here. So let me take the wire. This is the wire, and this is the current I flowing through that. See, here is the point P. See, which is at a distance r from the center. Now I just consider the area of cross section of the wire. And just this is the point, this is area of cross section, this is point P. Okay, point P is outside this wire, I is the current flowing through this wire, and let me take A is the radius of the wire. I want to know, this is R. See, in the first case R is greater than A. See, therefore the point is outside this. Let me consider the point somewhere here, point P dash. See, this is inside. See, to determine that, I must again consider Amperian loop. See, this is Amperian loop 1. This is Amperian loop 1. This is Amperian loop 2. Okay. Say this is solid wire. Solid wire. See, what is the magnetic field at P for R greater than A. R greater than A. Line integral of B dot dl is equal to mu naught into I. This, as usual, B line integral of dl is equal to mu naught into I. See, this is B into 2 pi r is equal to mu naught into I. RB is equal to mu naught by 2 pi into I by r. This is as usual. This is case 1. So let me take for point inside the loop. For R less than A. For A, R less than A. That means this is the point. That is the case. At point P dash. At point P dash. See, therefore, as usual, B dot dl is equal to mu naught into IE. See, here the current through this area, current through this region is less than this current. Here, if I take this as R1, let it be R, no problem. B into 2 pi R is equal to mu naught into IE. Here, IE is current density multiplied by I, pi r square. Current density multiplied by pi r square. What is current density of the wire? You know that what is current density? Strength of current in a given area, I by pi a square into pi r square. See, therefore I is given by r square by a square into I. Now you just substitute in this equation what you are going to get. Therefore B into 2 pi r is equal to mu naught into r square by a square into I. One r got cancelled. What you are going to get? B is equal to mu naught by 2 pi I by a square into r. See, this is magnetic field inside the wire. Have you got my point? For a wire of radius a, magnetic field due to current flowing in the wire inside the wire is given by mu naught by 2 pi I by a square into r. See, this equation tells you that inside the magnetic field it is directly proportional to r. Outside, magnetic field is inversely proportional to r. See, therefore if you take the variation of magnetic field with distance, if you take the variation B versus R, see, inside it will be like this. It is directly proportional up to A, R is equal to A, and outside it will be like this, R inversely proportional to B, inversely proportional to R. Inside B directly proportional to R. Therefore inside the wire magnetic field is directly proportional. Here I have taken current enclosed. IE stands for current enclosed by the loop. This loop encloses the current, not the total current. The total current is this much. See, this area encloses small current, lesser than that. See, therefore I calculated that current by considering current density in a given area. Current density is I by pi a square. In a given area is pi r square, where r is the radius of the Amperian loop 2. Okay, consider loop 2. See, here we have consider loop 2, here we consider loop 1. Consider loop 1. Have you got it? In this way we can understand how magnetic field varies with the distance inside as well as outside. So let us go for second application. Magnetic field at a point along the axis of a solenoid carrying current. We shall take a solenoid. At a point along the axis of a solenoid carrying current. First, let us understand what is a solenoid. Solenoid is a Greek term which means tube-like. Solenoid is a Greek term which means tube-like. See, it is consisting of a long tube whose length is at least 5 times its radius, 5 times its diameter. Whose length is at least more than 5 times its diameter. See, to that tube to that tube, large number of turns of copper wire is wound. Large number of turns of copper wire is closely wound. Is closely wound. Like this. See, when current is passed, magnetic field is produced. Magnetic field is produced along this axis of this solenoid. So let me take L is the length of this solenoid, and I is the current. The magnetic field is almost uniform. Magnetic field is produced along the length of the solenoid. Solenoid are the devices which are used to produce very high magnetic field in television, and even in synchrotron, a particle accelerator called synchrotron also makes use of solenoid. So many electronic devices make use of solenoid to produce very high magnetic field. See here, if you increase the number of turns, then the magnetic field produced also increases. The direction of the magnetic field can be understood with the help of right hand rule, Fleming's right hand rule. See here, you just cover this solenoid such that thumb pointing fingers indicates the direction of current and thumb points the direction of the magnetic field. See here, the direction along which thumb points corresponds to north, and this end corresponds to south. Say a solenoid is clasped with the right hand such that the fingers, if the fingers indicates the direction of current, then thumb points the direction of north side of this solenoid. See, therefore, see, if you redraw this, the schematic diagram would be like this. This is the schematic diagram. See, wherein I indicate the magnetic field by dotted line, and magnetic field lines are like this. See, this is the direction of magnetic field. Almost uniform field is obtained. Almost uniform field is produced along the axis of this solenoid. I want to know what is the magnetic field inside the solenoid. Okay. See, for that I just consider a loop, Amperian loop, with point P somewhere here, and the length of this loop is L. Let L be the length of this loop. Okay. Consider a solenoid of length L, and let N be the number of turns present per unit length. number of turns present per unit length. Let I be the current, let I be the current flowing through solenoid, flowing through the solenoid. Let I be the current flowing through the solenoid. I just take this loop as M, N, Q, R. I just take this loop as M, N, Q, R, M. Okay. See, this is the loop. See, therefore, to determine magnetic field due to this solenoid, I just imagine Amperian loop M, N, Q, R, M. Let M, N, Q, R, M be the Amperian loop. Amperian. Then what is the magnetic field due to this Amperian loop? Magnetic field inside the solenoid by considering this Amperian loop. Say this is equal to integral from M to N B dot dl plus integral from N to Q B dot dl plus integral from Q to R B dot dl plus integral from R to M B dot dl. Here you will be observing that NQ as well as RM are perpendicular to magnetic field line. So you know that B dot dl is B dl cos theta. Theta becomes 90 degree. See, therefore, magnetic field due to these two parts, NQ and RM becomes equal to 0. See, therefore, here magnetic field due to NQ B dot dl NQ is equal to R to M RM B dot dl equals 0 because B perpendicular to dl. Magnetic field and length element are perpendicular to each other. And if you take QR is external to this solenoid. Here magnetic field due to current entering and current leaving are in opposite direction and got cancelled. Therefore, there is no magnetic field external to this solenoid, outside this solenoid. See, therefore, here we have also found that magnetic field due to current flowing in the length QR, when you consider this is equal to 0. Why? Because B is equal to 0. Reason is B is 0. The net magnetic field outside the solenoid is 0. Then what remains? Only this part remains. So therefore integral of B dot dl is equal to M to N B dot dl. Only this much remains. And what is the length here? Length is L. So therefore, this is equal to B into L. See, this is B dot L. BL. Now you just make use of Ampere's circuital law. Ampere's circuital law says that B dot dl is equal to mu naught into I. See, here B dot dl is given. See, we have got this value B into L mu naught into I. See, I here is the current flowing in. See, if I take this as IE, see, IE here is here, IE is equal to N into L into I, the current flowing through only this particular length of the Amperian loop. See, therefore N into L into I, where N is the number of turns per unit length. Okay, I just take length as capital L. Okay, so that let me take this as capital L. There won't be any confusion. Then there won't be any confusion. N L into I. See, therefore we shall substitute this B into L is equal to mu naught N into L into I. See, L got cancelled, B is equal to mu naught Ni. See, this is the magnetic field at any point along the axis of a solenoid carrying current. Let me once again explain this. A solenoid is a long tube which is made of paper or which is made of any insulator, on which large number of turns of thin insulated copper wire is wound, such that the length of the solenoid is at least 5 times the diameter of the tube. When current is passed through the wire, a uniform magnetic field is produced along the length of the solenoid. Let me take the schematic diagram of this solenoid, and let P be a point inside the solenoid along its axis. So, to determine magnetic field at any point inside the solenoid, I just imagine an Amperian loop, rectangular Amperian loop of length L. Mn Q or M is the Amperian loop. Then, according to Ampere's circuital law, the line integral of the magnetic field around this loop equal to M to N B dot dl, N to Q B dot dl, Q to R B dot dl, R to M B dot dl. See, I have integrated that. See here, NQ as well as RM, dl here, length element is perpendicular to magnetic field. Magnetic field lines are like this. Length elements are perpendicular to them. Therefore, angle between them is 90 degree. Here B dot dl, B dl cos theta. When theta becomes 90, cos 90 becomes equal to 0. Therefore, magnetic field due to NQ and RM, the path NQ and RM equal to 0. And here QR is outside the solenoid. Outside the solenoid, magnetic field strength is very weak, and it is negligibly small. You can leave that. See, therefore, magnetic field is nearly equal to 0. Net magnetic field due to current incoming and outgoing got cancelled. See, therefore, field is approximately equal to 0 external to the solenoid. See, therefore, line integral of B dot dl from Q to R is taken as 0. What remains? The net integral is equal to M to N B dot dl. I just take dl, length of this segment, as L. So, therefore, B to L. From Ampere's circuital law, B dot dl is equal to mu naught into I. I is the current enclosed. See, current is there in a length L. If N is the number of turns, see, then we can write like this: I is equal to NL into I. L got cancelled, you will be getting mu naught Ni. Have you got my point? Suppose if the point is at one end of the solenoid, then it is almost half of this value. So, therefore, for a point P at one end of an ideal solenoid. In such a case, magnetic field is given by mu naught Ni divided by 2. See, this is an ideal solenoid. An ideal solenoid is one which has infinite length. I mean to say, its length is far greater compared to diameter. See, if that is the case, we call it as ideal solenoid. See, therefore, for ideal solenoid, at any point along the axis, magnetic field is given by mu naught Ni, and at the one end, mu naught Ni by 2. So, therefore, when you plot the graph of magnetic field versus the distance, the magnetic field is almost constant. It is almost like this. Simple. It's almost constant. See, therefore, you can produce uniform magnetic field inside the solenoid. Suppose if you keep any material like iron, ferromagnetic material like iron, nickel, cobalt, etc., they got magnetized. See, therefore, if the space inside the solenoid is filled with iron wires of relative permeability mu r, then the magnetic field is given by mu naught into mu r into n into I, where mu r is called relative permeability of the medium. Therefore, the magnetic field strength increases. If you keep iron wires inside, then magnetic field strength increases. It gets magnetized because iron has very high value for mu r. It's more than 1000. It has very high magnetic permeability, relative permeability. See, what is permeability? Ability of the material to conduct magnetic field lines through it is called permeability. Iron has very high value for relative permeability. See, therefore, we can produce strong magnetic field by keeping iron core inside the solenoid. See, therefore, iron core solenoid produces stronger field compared to air core solenoid. If there is nothing inside, we call it as air core. Air is present, air core. If iron is there, iron core. See, that's about solenoid. So now let us move on to the third important application, toroid. Let us consider third application, magnetic field at a point due to current flowing in a toroid. Due to current flowing in a toroid. What is a toroid? Toroid is a endless solenoid. It is a endless solenoid. If the ends of the solenoid are joined together, it became a ring. Okay. If the ends of the solenoid are joined together, it became a ring. Then it is called by special name toroid. See, this is a toroid. This is a toroid. See here, wires are wound. They are closely packed. See, wires are wound on it. this is a toroid. When current is passed through this toroid, magnetic field is produced. See here, to understand this, I just take a schematic diagram. See here, I take 1 Amperian loop, loop 1. Let me take radius 1. This is another loop. This is R2. Let me take another loop here. This is loop 3 and the radius is R3. Okay. To indicate the magnetic field, say magnetic field is perpendicular and towards you. Here magnetic field is like this. Sorry. Okay. See, now let us take magnetic field due to loop 1. See, when you take loop 1, for loop 1, see, this is V dot dl is equal to mu naught into IE. See here, this loop does not enclose any current because it is outside this. See, it is external to the solenoid, sorry, toroid. This is toroid, this is toroid, and whatever the loop 1 is present, this loop is outside this, in this region. See here, the loop 1 is taken. This is loop 1. It does not enclose any current. No current is passing in this region, within this region. See, therefore, here I is equal to 0. Here IE is equal to 0. See, therefore, this implies B is equal to 0. This is B into 2 pi R1 mu naught into 0, which implies B is equal to 0. Now let us take loop 3. Loop 3. See here, loop 3 is external to this. It is external to the toroid, external to the toroid. Here, as I told you in the last class, current entering and current leaving, they produces magnetic field in opposite direction such that the net field becomes equal to 0. See, therefore, in this case, the field itself becomes equal to 0. See, therefore, it has no meaning. B dot dl is equal to 0. Is equal to 0. Because it is external to the toroid. The net magnetic field produced due to current entering and leaving. See, they got cancelled each other and the net magnetic field is very, very weak. It is approximately taken to be 0. Suppose if you take the loop 2, for loop 2, if you take loop 2, see this is inside the toroid, see this is loop 2, it is inside, this is loop 2. See therefore B dot dl is equal to mu naught into IE, mu naught into IE. B is non-zero here, and what is dl? Dl is 2 pi r2, 2 pi r2 mu naught into, what is IE? See, IE is given by the total number of I is given by the total number of turns and the number of turns per unit length, all has to be taken into consideration for writing what is IE. See therefore here IE is equal to n into 2 pi r2, see that gives you total length, into I. See therefore B into 2 pi r2 is equal to mu naught into n into 2 pi r2 into I. What remains? B is equal to mu naught ni. See therefore even in case of this gives you what? This gives you, this is number of turns per unit length. This is the total length. See therefore what you are going to get? Total number of turns. See in that way B is equal to mu naught ni is the final result. See therefore even in case of a toroid, magnetic field is produced, magnetic field is present only along the axis, inside as well as outside the toroid. In a open space inside the toroid and outside the toroid, the net magnetic field is 0. See what is a toroid? Toroid is a endless solenoid. See it is consisting of large number of turns of thin insulated copper wire which are wound closely on a ring. When current is passed through the wire, magnetic field is produced along the axis of the toroid. Let us find out what is the magnetic field due to current flowing in the toroid. See here I have chosen 3 loops, Amperian loops, one inside the toroid, one the open space within the open space outside the toroid, and the third one outside the toroid. Okay, the magnetic field due to the loop 1 is equal to 0 because this loop does not enclose us any current. The magnetic field outside the toroid is very weak and equal to 0. See therefore magnetic field is contributed only by the loop 2. See therefore here loop 2, apply Ampere's circuital law, B dot dl is equal to mu naught into IE. Here IE is equal to, if n is the number of turns per unit length and 2 pi r2 is the circumference of the Amperian loop, then it is multiplied by I gives you current enclosed. So substitute in this equation, you will be getting B is equal to mu naught into Ni. See this is about toroid. Toroid also used to produce very high magnetic field in case of synchrotron, in a device called synchrotron. It's a particle accelerator. Solenoid as well as toroids are the integral part of most of the devices which requires intense magnetic field. See in fact for plasma confinement technique, say we are making use of toroid to produce very high magnetic field. So this is about the applications of Ampere's circuital law. See knowing of all this, let us work out some of the problems related to applications of Ampere circuit law. Please remember the toroid, in case of a toroid and solenoid, no derivation will be asked for the examination. From board examination point of view, there won't be any derivation, but you must know the final result. What is the magnetic field due to current carrying toroid and current carrying solenoid? Only both of them have same equation, B is equal to mu naught into Ni. Okay, now let us solve some of the problems related to Ampere circuital law. A long straight wire, a long straight wire, a long straight wire carries a current of, carries a current of 35 ampere, 35 ampere. What is the magnetic field? What is the magnetic field? Magnetic field at a point 20 centimeter from the wire, 20 centimeter from the wire. See, here is a long straight wire and this wire carrying a current, and here you want to determine what is the magnetic field at this point. Say this is at a distance 20 centimeter. So you know that B is equal to mu naught by 2 pi I by R. R I can write like this, B is equal to mu naught by 4 pi 2 I by R. See here, what is mu naught by 4 pi? Mu naught by 4 pi is equal to 10 raised to minus 7 Henry per meter. And what is I? I is equal to 35 ampere. I is equal to 35 amperes. And the distance R is 20 centimeter. R is equal to 20 centimeter or 0.2 meter. Now substitute this. B is equal to 10 raised to minus 7, 2 into 35 divided by 0.2. So this comes out to be 3.5 into 10 raised to minus 5 Tesla. B is equal to 3.5 into 10 raised to 5 Tesla. Right? Now let me move on to next problem. A long straight wire carries a current of 50 ampere. 50 ampere. 50 ampere. In north to south direction. In north to south direction. North to south direction. Give magnitude and direction of B and direction of magnetic field at a point 2.5 meter east of the wire. See here, current flows from north to south like this. This is north, this is south. What is the current? Current I is equal to 50 ampere. And See, let there be a point here in the east. Say this point is at a distance 2.5 meter. This is R. So you have to find the direction. You have to find the direction. The direction is can be obtained by using, so right hand clasp rule. Okay, so it can be obtained using right hand clasp rule. So you will find that it is vertically upwards. The direction is vertically upwards. So let us make simplification. I here is 50 ampere and the distance is 2.5 meter. V is equal to 10 raised to minus 7, 2 into 50 divided by 2.5. This is 100,040. So this comes out to be, so this is 100. If 1 point goes there, 1000 by 25 is 40. 4 into 10 raised to minus 6 Tesla. 4 into 10 raised to minus 6 Tesla. Using right hand clasp rule, direction of B is vertically upwards. Let us take third problem. A horizontal overhead power line, carries a current of 90 ampere in east to west direction. What is the magnitude and direction of magnetic field? 1.5 meter below the wire, below the line. See here there is a power line. So it is carrying current from east to west. How much? 90 ampere current. Okay. See, the current is flowing like this. This is the current. So what is the direction of magnetic field? It is acting in this direction. See, towards south. See, here they have asked you to find out magnetic field. The distance is 1.5 meter. So therefore now you come to know that this is east to west. This is north south. You just clasp this with right hand, okay, like this, thumb pointing the direction of current. The direction of this figure is south. okay, south, towards south. Therefore direction of magnetic field is south. See here, current is 90 ampere, distance is 1.5 meter. Now substitute here, two into 90 divided by 1.5. This is how much? Say this comes out to be 1.2 into 10 raised to minus 5 Tesla. And using a right hand clasp rule is towards south, the direction of the magnetic field is towards south, north to south, using right hand clasp rule like this. They are also asked in competitive examination, these questions. A long straight solid conductor, a long straight solid conductor a long straight solid conductor of radius 5 centimeter, carries a current of 2 ampere, which is distributed throughout the cross section, Find magnetic induction, at 3 centimeter, from the axis of the conductor, See, this is the conductor, this is the cross sectional area. Okay, here the radius is 5 centimeter. They ask you to find out this at this point. See, this is at 3 centimeter. See here, you just imagine an Amperian loop containing this point P. See here, current is passing. How much? Current of 2 ampere is flowing, 2 ampere. So you know that magnetic field inside the wire, inside the conductor B is equal to, it is given by mu naught by 2 pi I into R by A square, or I can write like this, mu naught by 4 pi 2 into I into R by A square. Here you know the value for mu naught by 4 pi. How much? 10 raised to minus 7. 2 into I is 2 ampere. What is radius? 5 centimeter. 5 into 10 raised to minus 2. And A 3 centimeter. 3 into 10 raised to minus 2 whole square. Okay. On simplification, you will be getting 4.8 into 10 raised to minus 6 Tesla. See, therefore inside the magnetic field is very small because current is lesser inside. See, that's why magnetic field decreases. Okay, these are all the problems which are related to magnetic field due to current carrying wire. Now let me take up solenoid and toroid. A solenoid of length 0.5 meter has radius of 1 centimeter and is made of 500 tons. It carries a current of 5 ampere. What is the magnitude of magnetic field inside the solenoid? See, you know that for a solenoid B is equal to mu naught into Ni. See, what is mu naught here? Mu naught is equal to 4 pi into 10 raised to minus 7 Henry per meter. N is number of turns per unit length. Solenoid has 500 turns. This is N by L. N is 500 divided by 0.5. This becomes 1000 tons per meter. And what is the current? Current in the solenoid is how much? 5 ampere. See, therefore V is equal to 4 into 3.14 10 raised to minus 7. N is 1000. This is 5. See, this comes out to be 6.28 into 10 raised to minus 3 Tesla. 6.28 into 10 raised to minus 3 Tesla. A solenoid 1.5 meter long and 4 centimeter in diameter. 4 centimeter in diameter possesses 10 turns per centimeter. 10 turns per centimeter. A current of 5 ampere a current of 5 ampere flowing through it, flowing through it, flowing through it, flowing through it. Calculate magnetic induction, magnetic induction A inside the solenoid, inside the solenoid B at one end phase along the axis, along the axis. Okay. See, first let us take up what is the magnetic field inside the solenoid. See, here they have given number of turns, how much? 10 turns per centimeter, 10 turns per centimeter, 1 centimeter. 10 divided by 10 raised to minus 2 meter is equal to 10 raised to 3 turns per meter. And again, what is the current? 5 ampere. So you will be getting the same answer. See, this comes out to be same. And what is B? At one end of the solenoid, magnetic field is B by 2. See, this is equal to 6.28 into 10 raised to minus 3 divided by 2, 3.14 into 10 raised to minus 3 Tesla. See, this is at one end of the solenoid for an ideal solenoid. See, this is ideal. See, length is 1.5 meter, diameter is 4 centimeter. Compared to 4 diameter, length is very large, therefore it is an ideal solenoid. So now let me take up problems related to toroid. A toroid has non-ferromagnetic core, has non-ferromagnetic core of inner radius of 0.2 meter and outer radius 0.25 meter, around which 1500 tons of the wire are wound. If current in the wire is, if current in the wire is 2 ampere, calculate magnetic field inside the toroid, outside the toroid. So you know that magnetic field at any point inside the toroid is given by B is equal to mu naught into Ni. See, we have to find out what is n. See, this is given by mean radius. Mean radius is equal to r is equal to r1 plus r2 divided by 2. 0.2 plus 0.25 divided by 2. This is 0.225 meter. 0.225 meter. See, therefore, what is n? N is equal to total number of turns divided by 2 pi r. N is 1500 divided by 0.225. Okay, turns per meter. And I is given. I is how much? I is 2 ampere. Now substitute in this relation. B is equal to 4 into 3.14 10 raised to minus 7 1500 by 0.225 into 2. See, on simplification you will be getting, it is about 3 into 10 raised to minus 3 Tesla. This is approximately 3 into 10 raised to minus 3 Tesla. Please check up this value. And the second thing is, what is the magnetic field outside? Outside the toroid is 0. Any point external to the toroid has net magnetic field equal to 0. Okay, it may be within the toroid, in a region within the toroid, or outside the toroid. See, this is along the axis of the toroid. Region which is external to it. A toroid has a core which is non-ferromagnetic. That means no iron wire or iron like material is kept inside. Okay, inside the core, non-ferromagnetic. Of inner radius 25 centimeter and outer radius 26 centimeter, around which 3500 turns are wound. If the current in the wire is 11 ampere, if the current in the wire is 11 ampere, what is the magnetic field? What is the magnetic field? Magnetic field A, outside the toroid, B, empty space surrounding inside the toroid, C, empty space surrounded the toroid. See, in A and C case, in case of A and C, you know that net magnetic field is 0. Any point outside the toroid or empty space. See, if this is the case, if point is, this is toroid. Okay. See, here point P is here, Q is here. At P and Q, net magnetic field is 0. There is no magnetic field. And let me take B. B is equal to mu naught Ni. See, here what is N? N is equal to, N can be found by considering total number of turns divided by 2 pi R1 plus R2 divided by 2. See, this gives you what? 25 plus 26 divided by 2. So you will be getting 0.255 meter. See, this how many turns are there? 3500. And I is 11 ampere. Now substitute in this equation, B is equal to 4 pi into 10 raised to minus 7. N is 3500 divided by 2 pi into 0.255 I 11. See, here pi got cancelled. See, now on simplification you will be getting 3.02 into 10 raised to minus 2 Tesla. So the magnetic field at this point comes out to be 3.02. Please work it out and check the final result. B is equal to 3.02 into 10 raised to minus 2 Tesla. See, in this way we can solve problems related to a current carrying straight wire, a solenoid and a toroid. Okay, I hope you have understood both the theory as well as problems related to solenoid and toroid. Let me stop at this stage. Thank you. Continue in the next class.